Hi folks, this is Mr. Murphy here. I want to do a video on section 1.2 for honors geometry. That's use segments and congruence. A couple things before I start. You may notice the time here, where it's about 10:20 at night. This is my second time doing this video because the first time it didn't have any volume, so if I sound burnt out, it's because I am. Also, if you hear any munching or chewing in the background, that's my dog, and he has a toy to occupy him. I know it's not exactly ASMR, but it is better than the alternative, which is probably barking, so we're going to have to deal with it together. Depending on where we left off in class, some of this may be something you've seen already, and if that's the case, feel free to sit through it again or just breeze past it. But I'm going to start from the beginning with some review from section 1.1, which deals with points in space and how things intersect and interact, and what is collinearity and coplanearity. Coplanearity? I don't know. Anyway, from the top. And by the way, if you want to try this on your own, like if you don't want me to spoil it, then just, you know what, pause the video, give things a shot, and then resume when you're ready. But I'm going to start with these questions right now. Are points H and S collinear? Well, here's H, and here's S. The answer is yes. The answer is yes because, without even looking at the diagram, I know that what it means to be collinear is that, if I'm talking specifically about 2 points, there will be a line that intersects both of those points at the same time. That's true if I'm talking about whether or not 3 points are collinear. Can there exist a line that passes through all 3 of those points at the same time? And in this case, and in every case with 2 points, the answer is a definite yes. In fact, that's one of, there's an old mathematician by the name of Euclid who's considered to be the father of geometry, and he came up with a postulate, I'll discuss what those are in a second, that basically says, if there exists 2 points in space, then there also exists a line that can pass through them. Think about it. Why can't I draw a line from any one point in space to another? And if you need to see that actually demonstrated, I'll do the best I can drawing on a trackpad, but here is a rough version of the line that goes through H and S, aka line HS. That's a big fat yes. Not just because I can draw the line, even though just because a line isn't there doesn't mean it can't exist. But even without that, just in general, are points blank and blank collinear, regardless of the diagram? The answer is always going to be yes. Using that same logic, if I'm talking about any 3 points, like H and E and Q. So let's try connecting them first. Here's H, here's E. That was a little sloppy. Let me do that again. And then Q is on the bottom right. So you may be thinking to yourself, I don't see the plane that goes through these 3 points. But it definitely is the case that such a plane exists. If I were to connect E to H to Q, what it would make is a triangle, obviously. And triangles are planar objects. Like a plane can pass through a triangle, so why wouldn't these 3 points be coplanar? If I think about this in terms of like the spatial relationship of a room, what I can essentially have is, like, imagine I have a drape or like a sheet that I just drape from the top corner of the room to the opposite bottom corner of the room. That sheet would essentially ask as a plane. Remember, I can't show the notion of infinity, but imagine this plane extending infinitely. Yes, I have a plane that passes through H and E and Q. So any 3-point orientation is either going to make a line if they're collinear, like if Q happened to be right here between E and H instead, in which case, yeah, I can see 2 planes that go through it already. If it's not going to make a line, then it's going to make a triangle, and a plane can pass through a triangle, so yes. Similar to the first question, any 3 points are going to be coplanar. Ingrain that in your mind. For the next one, name 4 non-coplanar points. So in other words, I want to pick a set of 4 points such that there cannot and does not and will not exist a single plane that passes through all 4 of those points simultaneously. Assuming that you've taken time to pause it if you want to think about it, let me just jump straight into saying, let me show you a little trick. A good way to figure this out for non-coplanar points is just pick 3 points that establish a plane right off the bat. So what about P and R and S? And now the trick for making sure that these 4 points are not coplanar is just pick a 4th point that we know is not on the same plane as these. Like, once we pick 3 points that are not in the same line, right, as these aren't, we've already established a plane. So really, we can just pick a 4th point that we know is not on it, like F, or G, or H, or E. So for instance, P, R, S, G is a set of 4 points that are not coplanar, and it should actually be obvious. Try to imagine a plane intersecting these 3 points on the bottom as well as G. Wouldn't work out too well. Similarly, G isn't necessarily the problem. It depends on the way I think about it. There's definitely a plane that passes through R and P and G. It would go like, it'd be the same as my sheet going from one corner to another, but in the opposite way diagonally. S wouldn't be on that. So no matter what way we cut it, this selection of 4 points or this selection of 4 points is a set of not coplanar points. So along the same line, like I seem to be making some generalizations here about when there's 2 points and 3 points and coplanarity and whatnot. Are collinear points always coplanar? Basically, if I have a set of points that lie in a line, do they also always lie on a plane? At least one plane, I should say. The answer is yes. So what if I have like P and Q, and let's suppose I throw a T down here, and T happens to be on the same line as PQ. T is on line PQ. These 3 points are collinear, definitely. By definition, they are that. And then if I want to ask if they're on the same plane, yes, they are. P and T and Q are on plane PRS, like the floor of this room. They're also on plane EFQ, the wall of this room, so to speak, the wall facing us most closely. So yeah, very clearly, because multiple planes can pass through a single line that these 3 points would sit on, yes, collinear points are always coplanar. What if I go backwards with this? What if I ask if coplanar points are always collinear? Notice the word always, which means if I want to disprove this conjecture, if I want to undo an always statement, all I need is one counterexample. So can I think of some points that sit on a plane but not the same line? And the answer should be an easy no. It is not the case that coplanar points are also collinear. Look at these 3 points. Look at how coplanar they are. Look at this plane that they sit on, the floor of the room essentially. Do P and R and S also sit on the same line? Heck no. I can't draw a line that passes through all 3 of these points. In order to connect them all, I'd have to add some curvature, in which case it's not a line anymore. So big fat no for this last one. So finally moving on to new content. Section 1.2, use segments and congruence. I may have dipped into this a bit in class, maybe not, but one of the big things that's big in geometry, like one of the defining characteristics of this class, is the fact that we look at the building blocks of math, basically. Essentially, what we use to kind of deal with the abstract notion of algebra, where all those things are derived from, how to add essentially coordinates to the world and look at how things interact with one another. That's just geometry. And if we are to try to make sense of things, what we want to do is we want to use logical deduction. And in order to logically deduce things, we need a framework. We need tool belts, essentially. Or I should say, we need some tools in our tool belt. Did you hear my dog cough? He's fine. So, it's fine, buddy. Just ate his tree too fast. So, when I say things like postulate and theorem, you maybe have never heard of what a postulate is before, but you've definitely heard of at least one theorem, right? The Pythagorean theorem, a squared plus b squared equals c squared, if I have a right triangle. I could prove that if I wanted to. I could blow all your minds. It's probably not that impressive. But anyway, I could blow all your minds and show you a proof of the Pythagorean theorem that would probably satisfy you within a reasonable doubt why that equation is true. That's because theorems are provable. And, some things have to be provable in geometry using some other geometric conjectures. And you know what? I could probably justify every step of the way as to why any step I use in particular is true. And I can keep going down and down saying this is true because of this. And then that also happens to be true because of that and that. So, a nice little side story. There's a comedian who goes by the name of Louis C.K., who's done rather nefarious things in the last couple of years. Don't look him up. But one of his jokes from many years ago was that he went to McDonald's with his little girl, his child, and they were like eating food or whatever. And the little girl asked him, "Can we go to the park when we're done here?" And he said, "No, sorry, we can't." And she said, "Why?" And he said, "Because it's raining." And she said, "Why?" And he said, "Because water's falling from the sky." And she said, "Why?" He's like, "I don't know, like water in the clouds." And she's like, "Why?" And he's like, "Because of vapors. I don't know." And she's like, "Why?" And he's like, "Why don't I know? I don't know, because I didn't pay attention in school." And she's like, "Why?" And he's like, "Because I was a bad student." So basically, we could be that little girl in geometry, and if I tell you something, you could be like, "Why?" And then I'll have to say, "Because that." And then you say, "Why?" And I say, "Well, because of this." And then we can go on and on and on. And we could do this for literally ever and be unproductive and never actually get to square one. So what we have to do in geometry is we have to make a square one. There has to just be something that we accept as truth. we call those things postulates. Postulates are statements that we safely assume to be true for the purpose of using them as the building blocks for our other arguments for justification in the future. So I name-dropped the man Euclid before. He is the father of geometry because he basically used, I think, a set of 30-something rules, maybe 37, that he called axioms, by which if we allow these basic assumptions about the universe to be granted as true, we can basically show anything related to math and calculus and physics and algebra, anything really. And that's withstood the test of time. He was around in like the BC days. And Euclid's axioms are still taught in college courses to this day. We can use those postulates to act as tools for proving theorems. This is what separates postulates from theorems. Postulates are statements that we can assume to be true for basic reasoning purposes. The theorems are the things that we can actually prove using postulates and previously proven theorems as our tools for doing so. The postulate is like the blueprint for our house, or it's like the building materials that we use to build up with it. So if I'm telling you to believe something, if I'm literally just saying, here's a postulate, shut up and believe it, just because I said so, that's really the reason why we believe postulates. They better be things that are very intuitive and very believable and very easy to understand. So I'd like to think that that's the case when we examine our first postulate, which is called the ruler postulate, which basically says that any point on a line can have coordinates, and those coordinates essentially measure its position. So think about a point on a number line. That has some point. I can plot any point on a number line, certainly. Even if I think about a point on a coordinate plane, then it has two coordinates. An x-coordinate to measure its position left and right of the origin, a y-coordinate to measure its position north or south of the origin. A point can have coordinates, certainly. If I want to find the distance between 2 points, I take not just the difference, but the absolute value of the difference to ensure that any measurement I get comes out positive. That's right, distances have to be positive. Because if I were to say, like, I'm -3 feet away from my laptop, that'd be a very strange statement, and that would be hard to interpret because distance can't be negative, thus the absolute value. So note here that when I talk about the measurement of segment ST, I don't have a bar over this ST. I've made a pretty big deal about this in section 1.1. Hang on a minute, sorry. Benji, cut it out. Benji, screwed up my video, buddy. But if I'm talking about the length of the segment or the distance from one endpoint to another, I don't have a bar over the letters. This is kind of a big deal, and it's how we distinguish a geometric figure from a number. If I'm talking about a segment, that is a geometric figure, and we make that distinction by throwing the bar over the letters. If, however, I'm talking about the length of that segment or the distance from one endpoint to another, then I don't include the bar over top, and I refer to it as a number instead. So basically, one of these is a shape, one of these is a number. I wouldn't say shape equals to. Like, it'd be weird to say this square is equal to, like, 5, or whatever. That's nonsensical, because figures can't be equal to something. This segment is 5, I guess sounds a bit better, but if I say this segment's length is 5, if AB equals 5, now that makes more sense. That's grammatically correct. That's appropriate. So, the second postulate, which we use quite a bit, so much so that we actually give it a nickname, the segment addition postulate we call the SAP. Or at least we will in the future. It's very sensible. So take a look at this segment that I have, the big one, AC. If A and B and C are all on the same line and B is in between A and C, I can break this up a couple ways. I could say that segment AC is, I guess we could pause it and try to figure it out on our own, but I'll straight up tell you. The way it relates to the other segments, A, B, and BC, is that it looks like if I combine these two smaller segments, then I get the big one. This postulate is exactly what it sounds like. If I have a couple segments, then basically the sum of the parts equals the whole. I could show this with actual numbers, like say that this AB is 7, say that BC is 6. That tells me that AC is going to be, you guessed it, because it's not hard, but 13. The sum of the parts equals the whole. But the fact that I'm now using AB and BC and AC to refer to numbers kind of allows us to treat them like variables. I know I could say like x plus y equals z or something, but these are labels that I can give segments that actually make sense. It's less arbitrary than calling it x. So again, in terms of variables, I can say segment AC is equal to segment AB plus, and again, sorry if this is sloppy, I'm drawing it on a trackpad, though. It's a lot harder than it probably looks. AC equals AB plus BC. And remember, there's no bars over these because I'm doing arithmetic with these things. They're actual numbers, not the figures, so no bars here. Problem time. Pause it if you want to, but I will proceed. If the totally real town of Fakesville, don't Google it, it's not actually real, spoiler, but I'll call it point F. If Fakesville is collinear with points L and T, Lubbock and Tulsa, and it's halfway between them, first of all, plot Fakesville on a map. We'll just kind of eyeball it, but I know we haven't gotten to this vocab yet, but I would call that the midpoint of LT. I will designate that with these marks, which I'm sure I'll talk about way later, but the fact that I'm drawing marks through these segments indicate that they are the same length, which means that I would have to cut the 380 in half, call it 190. So I should label this point, LF is 190, FT is 190, and then we were also told already that TS is 360 miles. Great. That's useful for part 2. Check with part 1. Part 2, find the distance from St. Louis to Fakesville. That's essentially SF. That is the length I'm trying to find, and in order to find this, you've probably done it in your head already. But I'm showing the excruciating detail here that with the segment addition postulate, this is probably the math that you're doing in your head. You're walking through this and saying, all right, so it's the sum of these two segments, FT and TS. I wish I could do this faster, but I can't. Not on the trackpad. So it's the 190 miles plus the 360 miles. How good is your mental math, folks? That is 550 miles. 550. And this is me being the math teacher, showing every step of work there is. I know you probably just added those two numbers in your head and you would have written down 515, that's fine. But what I'm doing is I'm showing everything in order to demonstrate that we've, even subconsciously, applied the segment addition postulate in order to add these values and get us something. So what is the name of the segment that represents this route? From F to S, that is segment SF. Notice that in this case, I'm not talking about the length of the segment. I'm explicitly asking about the segment itself, the geometric figure that is the line segment. So what's the name of the segment? It is segment SF. It gets a bar, whereas talking about its measurement, the length from, the distance from S to F, or the length of the segment, that's 550. Almost seems like a trivial distinction, but it kind of matters because of this page, when I talk about congruence. You may have been able to tell by the fireworks and the kind of GIF text that congruence is a big deal. So two figures are congruent when their measurements are the same. In other words, I have JK and I have LM. JK is 5. I can just count from -3 to 2. And then LM is also 5. Again, from 3 to -2. So both of these segments measure 5 units. So therefore, by definition, these two segments are congruent to each other. And again, this is the way that I say the measurements of two shapes are equal to each other. It might sound weird to say this triangle is equal to this other triangle. Equality is usually a number that we use for comparative purpose, it's a phrase that we use when we're talking about comparing numbers, and figures are not numbers. So the formal, mathy, geometric way that I would say that two segments are the same, or any two geometric figures are the same, is to talk about congruence, the symbol for which is this. Basically an equal sign with a little squiggly over it. So this right here is indicative of equal measures. Oh, this is going to take me forever to write, I just know it. Equal measures. Whereas the congruent statement to the right is not talking about equality, not talking about equal measures, but talking about congruent figures. Lest we're here forever, I'm probably just going to use shorthand here. Congruent figures. In order to get a little acquainted with writing congruent statements as opposed to equality statements, I've set up this problem on the bottom right here. Notice that this is the letters involved in pumpkin. I couldn't use the second P because I can't have 2-point Ps. That would get confusing. But yay pumpkins. Happy almost fall, everybody. If I want to make congruent statements as opposed to equality statements, I'm going to use this to demonstrate that being done. Just know that if you're going to pause it and try these problems, these bottom two are very, very tricky. And actually, some of you may not have learned the proper skills to do it now. It's one. But pause if you want to. I'm going to proceed. When I say fill in the blanks here, if I want to find out what PU is equal to, in this case I can just count. It's 3 units, right? So PU equals 3. Again, I'm talking about the measurement, the length of PU, so no bar over top. Same thing with SK. SK without a bar is essentially saying, what is the length of SK? Segment addition postulate says it's the 5 from the blue plus the 3 from the green. 5 plus 3 is 8. So this is 8 units long. If I were to ask which of these segments is 4 units long, let's see, it looks like to me. So UM is 4 units long. You could just count, and that's that. That's the first section. If I want to talk about congruent pairs, I'm essentially looking for 3 pairs of segments that are congruent to each other, that have the same length. So, okay, green and purple are both 3 units long. Therefore, we can say that PU is congruent to NK. So notice that when I'm writing this, PU is congruent to NK. I'm throwing bars over top now because I'm no longer talking about their measurement of 3. I'm talking about the fact that their shapes are the same. PU is congruent to NK. The other 2 are very difficult because they're not spelled out explicitly. Like, we'd have to do a bit of work to get there. I'll give you one, and if you want to find the other, cool. If not, check the answer key. But what I'd essentially have to do is look at some figures that aren't here. So PM, for instance, isn't drawn. But if I do draw it, it ends up being the hypotenuse of a right triangle. A right triangle with leg lengths of 3 and 4, as we've already determined. And if I want to know what the measure of PM is, segment PM, I could use the Pythagorean theorem. 3 squared plus 4 squared equals PM squared. 3 squared plus 4 squared is 25. If PM squared is 25, then PM equals the square root of 25, which is 5. This is a famous right triangle. This is the 3, 4, 5, because 3 squared plus 4 squared equals 5 squared. So if PM is 5, and SN is also equal to 5, that one's easy, we can just count it, then that means that segment PM is congruent to SN. And I know there's a third one out there somewhere, but as this video is already running long, I'm going to say you can find that on your own as a bonus exercise and call it quits for the night. So, thanks for watching, guys.